So this section is on an introduction to chemistry. Chemistry is often called the central science. You can sort of see all the things it affects: fields of biology, environmental science, geochemistry, agriculture. Chemistry is involved in nuclear chemistry and physics. There's certainly mathematics, computer science, all sorts of things, nanotechnologies. All these microchips are made using understanding of the chemistries of semiconductors, things like that. So we often call chemistry the central science. Physics is sort of more of a basic science than chemistry is. Principles of physics are sort of influence how chemistry is done. Really, historically, these subjects were different. The basic subjects are like physics, chemistry, and biology, thought to be completely different. And it wasn't until we began to understand what atoms are that we realized they're all actually very much related, and just fields studying different levels of complexity. Biological systems are way more chemically complex than typical chemical systems we look at. So chemistry is the central science. We'll talk about, over this full course, we'll talk about solids, liquids, and gases a lot. They're the typical phases of matter we're most connected with. Air is a gas, ice is a solid, and water is a liquid. As you can see, all are present in this picture. There's even liquid water in these clouds in the form of tiny droplets. And you can see how they appear in these are slightly different. Liquid water, gaseous water just appears as individual molecules. The little red molecules are the O, and the two little white ones are the H's. And then when ice bonds, it makes this weird little structure here you see in the second picture. And then liquid water is a little more, looks a little bit more like the gaseous water, except the molecules are a whole lot closer together. So of those phases, let's give some details on them. A solid has a fixed volume and shape, or rock, or any other solid object, the desk, the computer you're looking at, perhaps. Atoms in a solid can't change places or move relative to one another. That's sort of what defines a solid. A liquid has a fixed volume, but takes the shape of its container and has a horizontal surface on top. So you can pour water into a cup, or then you can pour it out, pour it into a bowl, or pour it into some other shaped object, and you'll see that it takes the shape of the object and leaves a flat surface on top. You can think of a liquid, if you want to think of the atoms, you can think of the liquid as a bunch of marbles, teeny tiny marbles. If you pour the marbles into a bowl, they'll more or less fit the shape of the container to the extent that they can, and give you a roughly flat surface on top. And they'll be right up against each other. Unlike in a gas where they'd be spread out, they're right up against each other in a liquid. In a gas, you have neither a fixed volume nor a fixed shape. A gas takes the shape of its entire container, no flat surface on top. It just fills up the whole container, and you can pour it into a larger container if you want. Whereas liquid always has a fixed volume. If you put it in a wider container, it'll be shallower. You take a cup of water, pour it into a wide container, it'll make a lower height. Not true with a gas. A gas will just expand to fill whatever shaped object it's contained within. So when we talk about chemistry, we're going to talk about chemical and physical properties. Physical properties are properties that are not associated with a change in chemical composition. And so we'll have to just talk a little bit about what that means. So physical properties are things like density, temperature, mass, color, boiling and freezing points, electrical conductivity. These things can be explored on an object without changing its chemistry. You can look at the density of an object or change its temperature or its mass. You can go take it through its boiling and freezing points without changing it chemically, bring it back to what it was. You can boil water and then recondense it. You can freeze water and then melt it, and it'll still be water. You can raise its temperature or lower its temperature. Those are all physical properties. Chemical properties are properties that are associated with the object when it reacts chemically with something else. And so when you're exploring a chemical property, you're actually changing the chemistry of something. And so examples of chemical properties are reactivity, acidity, flammability, toxicity, and more. If you set something on fire, you're going to change its chemistry. If you pour it in with something that it reacts with, like you mix oil and vinegar or something like that, you're going to change the chemistry. And sorry, not the oil and vinegar, baking soda and vinegar. You're going to change the chemistry of the two things. And so those are chemical properties. Reactivity, acidity, flammability, toxicity are some examples of that. In all of these cases, the object has to change chemically to exhibit the property. So a physical change is a change in a physical property. So you can heat or cool water, you can freeze or melt water, and so on. You can often change physical properties without changing the chemistry of the substance you're working with. A chemical change, on the other hand, is a change in a chemical property. And so an example of chemical change is iron rusting. It's no longer iron, it's now iron oxide when it rusts. Gasoline combusting. So when you light gasoline on fire in the presence of oxygen, you get carbon dioxide and water. Wood or anything else burning, those are chemical changes. Mixing vinegar with baking soda, as I said earlier, digesting food, rotting food, and so on. Those are all chemical changes. Other properties that we're interested in. Intensive properties is a property that does not depend on the amount present. This is a little weird, but it's a little different than what we've been talking about. So an intensive property is density or temperature or pressure. If you have something that's at 70 degrees, it doesn't matter how much you have of it, all of it's at 70 degrees. If you take a piece of iron, the density of iron, remember density is mass divided by volume, and so it's the mass per space it takes up. A little piece of iron has the same density as a big piece of iron. Lead is more dense than iron, or iron is more dense than wood. If you have a piece of wood, all the wood has the same density. All of a piece of furniture in your house has the same temperature, right? And so on. Pressure is the same way. The atmospheric pressure doesn't care how much air you have present. The pressure is the same all through the air. Those are intensive properties. Extensive properties is a property that depends on how much is present. So mass is an extensive property. Volume, total energy, number of atoms, those are all extensive properties. They depend on how much is present. And so these are just ways of sort of categorizing properties: chemical properties, physical properties, intensive properties, extensive properties. So two basic types of matter we're going to talk about: pure substances and mixtures. So anything you pick up on the planet is either a pure substance or a mixture. And so this is a little flowchart, and we'll talk about it more in detail. But you can say, does the matter have constant properties and composition? If the answer is no, it's a mixture. If the answer is yes, it's a pure substance. Sometimes this is hard to tell, and we'll talk about this as we go. If it's a mixture, then is it uniform throughout? That means it's homogeneous. If it's not uniform throughout, it's heterogeneous. If it's a pure substance, you ask, can it be simplified chemically? If it's yes, then it's a compound. If it's no, then it's an element. And so these are the four categories broken down of matter: heterogeneous mixtures, homogeneous mixtures, elements, and compounds. So we'll talk just a little bit more about them. So two broad categories are pure substances and mixtures. As we just talked about, pure substances fall into two categories: elements and compounds. Pure substances that cannot be broken down into simpler substances are called elements. You probably know these from the periodic table of elements. There are about 100 known elements. I think 90 of them are naturally occurring. The rest of them have really short lifetimes. Some don't last very long. You're familiar with many of them: hydrogen, helium, gold, silver, carbon, iron, cobalt, all kinds of different things. pure substances that can be broken down chemically are called compounds. Sodium chloride, which is salt, sucrose, which is table sugar, C12H22O11, water, carbon dioxide. These little chemical formulas, which we'll talk about more in the future, tell you the ratio of the number of atoms in each one of these compounds. All table salt has a 1-to-1 ratio between sodium and chlorine atoms. All sucrose, all sugar, those molecules have 12 carbons, 22 hydrogens, and 11 oxygens, and so on. 2-to-1 ratio between hydrogen and oxygen in water. So you can figure out the mass proportions in each of these if you wanted to by knowing what the mass of carbon atoms is, or hydrogen atoms, and so on. So here's a picture of the periodic table of elements. This is out of your textbook. I'll have it a few times in slideshows throughout the semester. It'll appear a bunch of times in the chemistry stuff we're doing. It's the same slide. It's the same periodic table, and we'll talk about it more and more as we go. The periodic table was developed first by, I think, Dmitri Mendeleev in maybe the 1850s or something like that. And he categorized these things in terms of how they behaved chemically, how they reacted with other things and other properties. And that's what made him create these things across the top, which you see groups. There are 18 groups across the top, and there are 7 periods. And by the way, this is all the elements we know. Elements that are bigger than the biggest ones here are extremely unstable. And so really the periodic table ends somewhere around here. You can, these ones up here at like 118 have extremely short lifetimes. You might be able to put together a bigger one, but you have an even shorter lifetime, and so it's almost nonsensical to talk about them. So if you look at the periodic table, the elements all have letter abbreviations. So H is hydrogen, He is helium, Li is lithium, Be is beryllium, and so on. If they're yellow, they're a metal. If they're pink, they're a metalloid. If they're gray, is that gray? They're a non-metal. If they're written in black, if the font is black on them, they're a solid, just in nature. If they're blue, they're a liquid. If they're red, they're a gas. You might have learned in your chemistry class in middle school that the right-hand column is the noble gases. Notice they're all red. Here's a blue mercury right here. Mercury appears naturally as a liquid. So does bromine. There are a few that occur that way just naturally. Most of them appear as solids. Over here on the right side of the periodic table, there are some gases. Nitrogen and oxygen are what you find in your atmosphere. There's also fluorine and chlorine. And so this is how you read the periodic table. Here's a symbol, right? This is the atomic mass, and we'll talk about that as we go. That's the name, and this one's called the atomic number, which we'll also get to. Back to our categories. That was elements, right? That was the periodic table of elements. Those were pure substances we looked at, elements and compounds. Now we're back to the other category, which is mixtures. In addition to pure substance, matter can be mixtures, and this is sort of the more common thing. A mixture is composed of 2 or more types of matter that can be present in varying amounts. And so a mixture that varies from point to point is called a heterogeneous mixture. So a heterogeneous mixture would be oil and vinegar, for example. Other types of salad dressing, anything with lumps in it, right? A bag of different types of rocks, sand and water, a bowl of nuts and raisins. The atmosphere, right? Sorry, not the atmosphere. The atmosphere looks uniform. So a heterogeneous mixture, you can see the 2 different types of objects or more inside the mixture. A homogeneous mixture is a mixture that is uniform throughout. And so examples are sports drinks, if you drink Gatorade or something like that, right? It looks uniform. You might even think it was a pure substance, but if you did some testing on it, which you would have to do to sort of figure that out, you would realize that no, there's water in there, and there's sugar in there, and there's food coloring in there, and other stuff that isn't really good for you. Salt water is another mixture. Ocean water would be a heterogeneous mixture because it has stuff floating in it, right? In fact, sometimes tap water you can see stuff floating in it. You might call that a heterogeneous mixture. Although most of the time we call water a homogeneous mixture if it's fairly clean. If you get bottled water, I would call that a homogeneous mixture. Air is another homogeneous mixture. Again, these are not pure substances because salt water has salt and water. Air has oxygen and nitrogen and carbon dioxide and argon and water and so on in it. So it's not a pure substance. And gasoline, which has a bunch of different types of hydrocarbon chains in it, and that I don't know any more about it than I just said. So here are some questions we can answer, right? What are the three phases of matter? Why is chemistry called the central science? What are the differences between solids and liquids and gases? What are physical properties and chemical properties? Give three examples of each. What are physical changes and chemical changes? Give three examples of physical changes or three examples of chemical changes. What are intensive properties? What are extensive properties? What are two basic types of matter? What are two basic types of pure substances? What are two basic types of mixtures? Give three examples of elements, of compounds, of heterogeneous mixtures, and of homogeneous mixtures.